Hey guys, today we'll be going over Codeforces round 1084, the Div 3 contest yesterday. If y'all are keeping track with my Codeforces Everyday series, y'all know I was able to solve A, B, and C, but as per usual, I always try to upsolve one or two problems, so I was able to do D and E. D over here is not marked as complete because it's currently in queue right now, and it's been in queue for a while, like an hour or so. I was going to wait for it, but it's taken quite a while, so I'm just going to make the video, and if D happens to be wrong, the answer is probably some permutation of what I have. So, yeah. I have a little script of, like, basically non-verbose ways of the problems, ways of reading the problems, so I'm not reading the entire problem for y'all. Y'all can go do that, but I will be providing my solutions to each of these problems. If y'all have questions, leave them in the comments. I'll also have timestamps for each of the questions if I remember to do them either in the comments or descriptions as well. So without further ado, let's get started. And I'll make an extra file, call it test.py. And this is where I'm going to be solving all the problems today. So, okay. Question A, eating game. There are N players sitting around a circular table. Player I has AI dishes to eat. Players take turns in order, and any player can start. On their turn, if a player still has dishes, they eat exactly one dish. Then the turn moves to the next player, clockwise. The game continues until all dishes are eaten. The player who eats the last dish wins. Determine how many players could possibly be the winner. So, for this question, it's pretty straightforward. It took me a little while during the contest to understand exactly what they were asking because of this I mod n plus 1 kind of reasoning, but you kind of realize pretty quickly that this is it just means the next player is going to start their turn. If you just plug in some numbers, for example, like for some of these cases, there's one player with 10 dishes, he's just going to go every turn, right? Two players with 6 to 7 dishes. I don't know what the contest creator was on about with 6-7 in this contest, but this showed up definitely multiple times. But yeah, basically what this is saying is each person is going to have their turn after the last. So it becomes pretty simple. We can take in some input, t equals int input, and then for in range t, we take in a line in equals int input, and then an array a equals list map int input split. And then basically what we're looking for is the player who eats the last dish is considered the winner. Determine the number of players that can possibly be winners. So what that means is it doesn't actually matter how much each player has. The player with the most will be the winner. So let's say the most is like 4. And all these like 1, 2, 2, 3. This guy will be the winner, right? Now, how can we have multiple winners? Well, we can have multiple winners if if the maximum happens multiple times. So this was a little confusing to me during the contest because I was like, in an eating contest, aren't you trying to like finish your dishes fastest? I didn't really understand the question. So, yeah, read the question, guys. But yeah, this is what we're looking for. It's pretty simple to code. You just find the max. So we can find max dishes equals max a, and then we just print a.count max dishes. And that's the answer. We can see for what I put during the contest, max dishes equals max a, print a.count max dishes. You can run it on the sample case and it passes. All right, moving on to B. deletion sort. You're given an array of A of n positive integers. Each turn, if the array is non-decreasing, the game ends. Otherwise, you remove any one element from the array. Find the minimum number of elements remaining when the game ends. So, this question is also pretty straightforward. Our inputs still it's the same inputs, so we can just delete this stuff. And now what it's saying is, if A is non-decreasing, that means A can not be A can be increasing. It can like be all the same. It can be like the same, then increasing, then plateau again, then increasing, as long as it's not decreasing, basically. So determine the minimum possible elements that can remain after the game ends. So for this question, you kind of have to just look at the test cases and play around with the test cases yourself, and you have to realize this. Like, there's a formula to solve this problem, but yeah, this is a greedy problem. So you kind of just have to realize the solution, and you can realize pretty quickly that you can check if the array is non-decreasing or not with A equals sorted A. Because what sorting does is it just arranges the array in a non-decreasing order. It puts all the small numbers in front, puts bigger numbers, blah, blah, blah. And this is just non-decreasing order. So what you need to do is realize that, like, if after playing with the test cases a little bit, like, make the minimal possible test case. So we can have this, like 1, 2, 4, 3. This is almost non-decreasing order. If we had 4 out of here, we would. But we want the minimal possible array, right? What's it asking? The exact words it's asking is, determine the minimum possible elements that can be remaining in the array after the game ends. So we're like, oh, we can pop 1, we can pop 2, still not non-decreasing, we can pop 3, and then we'll end up with 1 element. And you'll see pretty quickly that no matter what you do with like a standard array, you'll end up with 1 element. So why can't we just print 1 and be done? Well, there's a special case that we need to be aware of, and it's when the array by default is in non-decreasing order. So if it's 1, 2, 3, 4, by default, this is already in non-decreasing order. We can't just print 1 because this is 4. The game already ended, right? So to check for that, we check if A equals sorted A. So this is checking for non-decreasing order. Then we print the length of the array. Continue. Else we print 1. And yeah, that's it. Pretty simple question. Let's look at what I put in the code, and it's the exact same thing. A equals sorted A, print in, continue. Otherwise, print 1. Run it on the test cases, and it passes. All right, 2 problem C. Specialty string. You're given a string S of length n containing of lowercase letters. In one move, choose indices I less than j such that S1 or Si equals Sj. Neither character is star, and every character between them is star. Then replace Si and Sj with star. The game ends with when no valid move exists, and the AKS lol coding wins if every character becomes a star. Determine whether this is possible or not. So this is a pretty standard stack question. You realize pretty quickly that the first move you can do is, like, since the obviously the array doesn't start with any stars. The first move you can do is if two letters next to each other are the same. And then after that, you can kind of remove them from the string. Like, you don't really care about them anymore. You just want to determine if you can make the entire list stars. So when you remove them, it's like you just don't have to worry about them anymore. And at the end, you can kind of just check if the array is empty or not. So in order to do this question, what input do we take in? T. We take an N, and then we take in a string. S equals input. And yeah. Okay. So the first thing we need to do is let's remove all of this. We can define a stack equals array, and then for char in S, we add it to the stack. Or we would check if stack and stack -1 is equal to char stack dot pop. So what we're doing here is we check if the stack is empty or not. If it's not empty, then we have this last digit. We check like the last addition to the stack. We check if that's equal to the current letter that we're on in the string. If it is, we pop it out because that would be the character that we're replacing with the star. Otherwise, we would just stack dot append else stack dot append char. So if we don't end up popping it out, that means the char that we're going to add to the stack is different, and we'll just add it in. Now at the end, after we processed every single letter, we check if the stack is empty. If stack print. So if the stack exists, then we lost, right? So we print no. Else, print yes. Pretty straightforward problem. Not much to explain. Basically, process all the letters, and you just check the letter you processed before to see if it's the same or not. If it is the same, remove it. Else, just keep going. And then at the end, just check if the stack is empty or not. And let's look at what I implemented. Basically the same thing. All right, run it for the test cases. Passes. All right. Moving on to D, and this is where it gets a little bit difficult. I was not able to solve this during the contest, but afterwards, it's actually not that difficult. It's pretty simple, in fact. But yeah, let's read the problem. You're given a permutation P of length n and two portals at position x and y, where x is less than y. You may perform either of the following two operations as many times as you want. You can remove the element to the immediate left of one of the portals and insert it to the immediate right of one of the portals. You can remove the element to the immediate right and insert it to the immediate left. So here they have some examples here you can look at. But yeah, the goal is to find the lexicographically smallest permutation obtainable after any sequence of operations. So you can operate as many times as you want, you just want the smallest possible permutation. So for this question, the first thing you have to realize is your array, you're given two portals and an array. You can kind of split your array into the three slices. So for example, we have this array, and let's say we have a portal here and a portal here, right? We can kind of slice our arrays down into these portals. And then Now let's take a look at the behavior of this middle slice. We can send this slice, this element, through this array, and it'll pop out behind this element here. And then next we can send this one through, and it'll pop out behind again. We can also do the opposite. We send this guy through here, pops out here. This guy through here, pops out here, right? So you realize pretty quickly, this is a circular array. Like, the order of this array will always be the same, but you can shift it however you want. Like if you have 1, 2, 3, 4, you shift it, 1 goes back here, you have 2, 3, 4, 1, etc., etc. It's just a circle. Now to get this in lexicographic order, you really just care about the minimum. So we basically want to shift it till this first element here is min. Let's call this array mid. So min mid has to be the first element of this array. Now for the rest of this, we can kind of look at all this as one array. Let's just call it outer. Outer is like, this is x, this is y. So outer is from the beginning of the array to x, and then plus from y to the end of the array. Right. And then this, because like the behavior here is, the reason why we can do this, by the way, is because we can shift all of these, like we can put both of these elements into this array at the end, or we can put both of these into this array. It doesn't really matter. It's still kind of the same group of elements. And so what we're doing, what we're going to do is we're going to find the best slice to shove this mid array into. So for example, say we have 3, 1, and then we have a portal 4, 5, portal 2, 6. We treat this array as, we treat the outer array as one big array, and then our mid array, it's already in the right order for us. Where is the best place we can shove this array? Well, is 4 less than 3? No, so we wouldn't put it here. Is 4 less than 1? No, so we wouldn't put it here. Is 4 less than 2? No, so we wouldn't put it here. Is 4 less than 6? Yes. So this is the best place to put it. So that's the solution to this question. It's pretty simple. Keep track of your mid array, reorganize it to where the smallest is first, and then pick the best spot to put it into the outer array. So let's code that. Our inputs for this question is a little bit freaky. We are given we're given in, and I'm on the wrong problem. We're given in x and y equals map int input split, and then we're given an array which is list map int input split. We can remove all of this previous problem stuff, and then define an mid array. Mid array by default is from x to y. Right. We can just double check because I know Python has some weird like indentation rules that I should probably memorize, but I never really bothered to. Oh. T equals int input. For the past two problems, I did not put these parentheses here. Tragic. But okay, we can test just the first case, 404. Map int input split. There we go. Then we can remove one from each. Bug fixing in the tutorial video. And then, boom. So, oh, that's not good. Why did it grab every one? Oh, no, that's correct, because it's from 0 to 4. It should grab. Oh, this was a terrible case to try. We can try this one, 5, 5, 1, 3. And then these. So this should grab 1 and 5. 0, 1, 2, 3. Because there's a portal at here, in between 1 and 3, and after 5 and 2. So yeah, there we go. Now we can define, well, we can rearrange this array so that the minimum is first. So we can do that with min mid equals min mid. And then mid becomes mid from min mid to the end plus the beginning to min mid. Mid. What's going on? Was not closed. What do you mean? It clearly is closed. Hello? Beginning to min mid. Equals mid. From min mid to the end plus mid. Oh, I forgot the mid here. From the beginning to min mid. Okay, there we go. And then we can define an outer array, which is just from the beginning to x of a plus y to the end of a. And then for I in range, len outer, we check if outer I is greater than, because if it is, then we want to insert it at I. If outer I is greater than mid 0, we will print outer from the start to I plus mid plus outer from I to the end. And then we can put these in parentheses and put a star in front to unpack it, and then continue. There we go. I think this should be it. We can take a look at my code. Oh, there's one more part to look at. There's one more case where if our portals are just at the end and we only have the mid, then all we have to do is rearrange this. So after this, we can check if outer, len outer, is equal to 0, print mid, unpack it, and then continue. So yeah, if we look at it, we define an if. Why did I call this P? Did they have it as P? I guess they had it at P, but the array is P. Our mid is from X to Y of P, and then our like rearranged mid is from min mid to the end, and then we start at min mid to the end, and then from the start of mid to min mid. So there's just rearranging the circular array, and then finding our outer. So from from the beginning to X, and then plus P from Y to the end. And then we check if not outer, print star mid. So if outer is empty, I forgot that on this. Well, if len outer equals 0, same thing. We can also do if not outer to check if outer is empty. Print mid, unpacked, continue. Otherwise, we iterate through the length of outer, and if outer I is greater than our first element in mid, we print outer from the beginning to I plus mid plus outer from I to the end, unpacked, and then continue. And we can see it works for the given test cases, and it passed. Now let's see if... Oh, I got a wrong answer on this question on test 2. We can like debug it a little bit here. What happened? Wrong answer. First numbers differ. Expected 4, found 5. Participants output. So it's this first case here. Jury's answer is this. Well, I didn't expect this to happen. We're going to turn this into a figure out the question together type of video. Expected output 4, 5, 6, 2, 3, 1. We're given 6, 5, 4, 2, 3, 1. Our portals are at 1. So here, and then 3. 1, 2, 3. So here. So if we print out mid here, we should get 5, 4. Yep. Now we rearrange this to be 4, 5. And then we're left with 6, 2, 3, 1. Okay, I see what's happening, I think. If we print mid here, this didn't work. Why didn't this work? Min, mid is 4, right? So from okay. These are the reason why this didn't work is these are indexes. Or these are actual numbers. We need the indexes. So we're going to do mid dot index or mid dot find. Right, if I remember correctly. Run this. list, no attribute, find. I think. The dot index, the mid dot index. Oh, I did not mean to run that one. Print min mid. We output 4. Okay, print mid. 4, 5. There we go. Now, just remove this. Should be fixed. Okay, there we go. So the issue was, instead of grabbing the index of where we should start, I was just putting in the value of the minimum element of where we should start. Now, is there a better way of doing this? Maybe. Can I think of one off the top of my head? Not really. But yeah, let's submit it. Hope it works. If it's gonna be, oh, Jover. This is embarrassing. Expected 1, found 4. 13. I'm just gonna copy a bunch of these. So I don't know which one number 13 is, but this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. There's 25 of them. Then it didn't show up. 6. Okay, well, something obviously is logically wrong here, because 6s are going in the front. Let me think. Is it something wrong with my code, or is it something wrong with my solution? So so I think it's this case where it's 4, 2, 3, 1, portals at 1 and 3, where we have to insert it at the front. I think that's the issue right now. Oh no, it worked for this. Let me check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay. It fails on all these bottom cases here. The last 3, 1, 2, 3. Expected. But these aren't even the same, are they? They're not even the same length. here. We don't want these three. See the output. Or we want three more. Three, four, four, four. Received output. 3, 3, 4, 4, 4. Huh? Yo, what? Wait, even some of these first ones aren't right. 4, 6, 6, 4, 6, 4, 6, 4. This one isn't right. 1, 3, 4, 5, 2, 6. This is 1, 3, 4, 5, 2, 6. So number 3. Three. What? Why did I receive output for only 2 of them? Okay, well, we passed the first case. Past the second case, we don't output anything for the third case. So let's only look at the third case. We just don't output anything. We're on 3, 4, 6, 5, 2. 1, 3, 4, 6, 5, 2. We have a portal at 3, 4. 0, 1, 2, 3, 4. Okay, so our mid is 6. We check if outer I okay, if it is, else break print outer plus mid. One, 3, 4, 5, 2, 6. Delete this. Delete this. Still don't know what this is catching on. Failed for this. No, it's just this. No. Oh, this is the worst tutorial video ever. Two through one, but why are you printing 3 to 1 as well? We should break. Oh, we need to add a flag. I understand. Flag equals false. Flag is true. If flag. If not flag. There we go. End of file. What is this? Did I mess something up here? Okay, that should be it. There we go. We got it, guys. Okay, logic was there, just a few debugging issues, but we got it in the end. Alright, let's move on to the next problem. Problem E. Hopefully this one goes a lot smoother. Alright. Divisive battle. Alice and Bob play a game on an array A of n-positive integers. Alice goes first. On a turn, if the array is non-decreasing, the game ends immediately. Otherwise, the player may choose an element x and split it into y and z such that x equals y times z, and y and z are between 1 and x, non-inclusive. So, and then you would replace x with y and z in the same position in any order. If no valid moves exist, the game ends. When the game ends, if the array is non-decreasing, Bob wins, otherwise Alice would win. Assuming optimal play, determine who would win. So, little bit of a confusing problem, but we got it. Let me move this out of the way and close all of these. Alrighty. Now, for this problem, what we need to take note of is that Alice will win for the majority of the time. And like from the start, this is the same as the earlier problem. Was it problem B? Shoot, I forgot. It was problem B, I think. We want to check if the array was sorted by default. If it is, then Bob wins, right? So we should check this. Let's also take in our input in T, then we take in an A, then we take in another array. So if the array is non-decreasing by default, if A equals sorted A, then Bob would win. Right? Now, what we need to do is, like, this is the special case. This case gives you a big hint on how to solve this problem. Now, what we need to realize is 1, 2, 3, 4. Let's do 1, 2, 10, 3, 10, 10, 7. Let's do 1, 2, 10, 7. So we're given this array. Alice would go first, pick 10, split into 5 and 2, right? Alice can force Bob to lose on the first turn if she is able to make a prime factor, like if there's a number where you split it and there are two prime factors and one of them is greater than the other. Because since you can put them back in any order, it's in her best interest to always put the greater number first. Like even if it was like 1, 2, 8, 7, split this into 4, 2, it's in her best interest to try to put the bigger number first. Now in this case, this 4 further splits into 2, 2, and Bob still wins. But this brings up this example here. Now, for those of y'all who don't know what's going on here, this is a prime number, so this can't be split. This over here is 2 to the 13. So eventually it'll be 2, 2, 2, 2, and then 6, 7, 7. And this is a Bob win scenario. Now, what we can realize here is when a number is split, is like a power of another number, so k equals x to the y, we can just replace this number. We can replace k with x. So the array will give the exact same result as 1, 2, 6, 7, 7. This will give the same result as 1, 2, 2, 2. If you put all 13, 6, 7, 7, it'll also get the same result as the original array, 6, 7, 7. And in this sense, like you can kind of collapse arrays either way. Like if it's like 1, 1, 1, 2, 2, 2, 3, 3, 3, you can collapse this down to 1, 2, 3. It'll give the same result. Now, the question is, how do we find these special numbers? Because if it's the case where it's 7 to the 10, 6, 7, 7, 7 to the 10, or let's not use 6, 7, 7 here, let's use like 5. If we replace 7 to the 10 with just 7, Bob will still lose, right? Alice will win. So how do we find these numbers is what you're asking. So what we can do is we can define a function called prime factorization. We take in an input in, and what this will return is like the set of prime factors. I don't know, we need to import math for this one, so I'm just gonna do that real quick. And so we can define the factors as a set because we don't care about multiples. And while in mod2 is equal to 0, we want to add factors.add 2 in divide by 2. There's probably a faster way to do this, but this is, and there definitely is, but this is actually off of my prime factorization template that I made in today's video. This is just like, you can tailor this prime factorization function for this question. And because this wasn't made with a set in mind, like this is finding all factors. Since this one doesn't care, like you can technically optimize, like find a 4 and then, or find a 2 and then divide all of the 2's out. But I mean, this basically does the same thing. There might be a faster way to do it. I'm not going to put my mind into it. Y'all can look on it on your own time. So, and then for I in range, we start at 3 since we started at 2 earlier. And we only have to go to math.squirt n plus 1. Because the reason for this is once you get to that square root of n value, the factor it's multiplied by is probably either square root of n or under that. Because if you think about it, numbers after that, numbers higher than square root of n will be numbers that can either be like broken down further, or like you basically already visited it. Like there's just no factors that are like, if you think about 10, it's 5 and 2. There's no factors like you can't use 7 or whatever. Yeah, you get the point. N plus 1, and then we increment by 2, and then while n mod I is equal to 0, factors dot add I. So we increment by 2 to skip the even factors since we don't need to check those. And then n double divide equals I. And then there's 3 cases. If n is greater than 2, we should return, or we should factors dot add n. So this is just to add like the leftover factor after all the divisions. Now there's 3 cases. If the length of factors is greater than 1, we return -1. If the length of factors is equal to 0, so this specific one catches when n equals 1. We return 1. And okay, so let me explain these. This catches if there's duplicate, or if there's multiple factors. If there's multiple factors, like for example 10 that we showed earlier, then Alice can always force a win, right? And we will have a special check for -1 down here when we solve the problem. But this is to check for if n equals 1, just return 1. And then finally, if none of these cases, return factors.pop. So it will only return factors.pop when there's only one factor, right? And we want that one factor. And then, oh, where did everything else go? Okay, so print Bob continue. Now we can define a factor array. Factors array down here, and loop through for element in A. Factors dot append prime factorization element. So what this does is we go through every single element, check for its prime factorizations, and we record them all into this factors array. And then if the min in factors is equal to -1, so this is our special case, then we can immediately print Alice. Because this means she has a way to force Bob to lose. Else, okay, this should be all in the same indentation. Elif factors equals sorted factors. If you remember from earlier in the question, if the array is equal to the sorted array, then it's non-decreasing, which means Bob wins. Finally, if it's not non-decreasing, print Alice wins. And that's the whole problem. It's a pretty long one. I think you just need to be familiar with this prime factorization, how to find prime factorizations for this problem. And yeah, my code over here, as you can see, I basically copy and pasted my template and then modified it a little bit. Oh, yeah, I copied and pasted my template and modified it a little bit to fit my needs. And yeah, basically the same thing. We can run it for the test cases. There we go. There we go. And we pass. So that's it. That's the end of this video. Sorry it's a little sloppy. It's my first type of like tutorial-esque type video. Didn't really have a script for it, so and we got a little off track with what was going on with problem D. But if this helped you and y'all enjoyed this kind of video, be sure to like and subscribe. I plan on doing more of these for the future contests, just so I can review the problems that I've done and like make sure they sink into my memory of how to do them, as well as helping y'all, those of y'all who couldn't solve a particular problem and need a video solution for it. That's what I'm here for. If y'all enjoyed, like and subscribe. I'll see y'all guys next time. Bye.